So just before, I'll just give a little bit of introduction of where I am. So I'm quite far away. Natal is a tourist region in Brazil, very touristic in some sense. So I'm not from there. And when they invited me, I was very welcome. So basically, we are here on the northeast part of Brazil. They say that's the place where the Portuguese arrived, but they just went down, they say. But it's a very nice place that is further away from Rio. So when you are going to Natal and you ask, can we do a short pass in Rio? It's like a 3-hour flight. So it's quite far away. But just to give just a glimpse about our university. So we are kind of a new university also that's very thematic in some of the areas you work. And it's by the season. It's not bad, the weather and everything. And the place I work is kind of innovation center, like here, that is fairly new. And we basically work with many works with industry and basic research. But our main basic research is from our area here, that it's biome, where it's one of the centers. We have that, and it's basically where I can. But the nice thing about all of this is that this is a very interdisciplinary area, and disciplinary building program and everything. So here in our bioinformatics centers, we have professors from the psychology, from the neuroscience, from the biochemistry, and from the IT or computation. So that's a really interesting place to be, and we are open for positions for professorship this January. There's anyone like sunny weather all year round. So let's speak a little. So let's go to the topics. So the subject of interest for me in the recent years is essentially brain diseases or brain disorders in general. We've been tackling many of these diseases in many ways, so it's not a very small topic. It's very broad in some sense. Like we started working with data from Alzheimer's disease, and I worked with Parkinson for some time. And nowadays we are also starting to look into mood disorders, depression, etc. So this will be very general in this term. So I'll be changing diseases sometimes, so sorry if this goes the wrong way. But from the point of view of engineering, from the technology, this is a very big problem, and from the economics, in the sense that this is a general problem. If you take the numbers, the amount of people that economically won't be producing because of that, and also the impact in the quality of life, which is the social part is huge. So it's something that's quite appealing when you're working with technology, because the scale of technology might be an interesting way to tackle this kind of problem. And the biggest issue about this, about working with mental health, is because it's very labor intensive way to actually treat people. So nowadays, I had once I actually got my position at the university, I had to find a psychiatrist to give me a report saying, "Oh, you're not, you're capable of working." I couldn't find on time because they gave me 30 days to find a psychiatrist that could know me, examine me, and give me something right. Like even in the private, because Brazil has a mixed system. Like we have the SUS that is very related to NHS. But since Brazil is huge and not so rich, so we rely a lot on the private system as well. But even in the private, I couldn't find it. So I just got it because I knew a person whose wife was a psychiatrist, and then she gave me in the last day because of the law and everything. And I ended up working with her, so actually it was quite good for that. But the key issue is really scale. Like if you take Brazil, I was in a capital state, so it's a place that I can actually find a psychiatrist. But if you're like in the countryside, like a 4 hours bus to the main big city, it's definitely something hard to work with. And also there's very few doctors that work in psychiatry. That's in Brazil. And I think this is probably a general problem. Every time I speak about this, like the social workers, they normally, yes, it's very hard to find them. So it's definitely a problem that's very appealing for working with technology. So, but what's the main issue? Now think about the point of view of engineering, about of problem solving. What's the biggest issue of mental diseases? The first thing is that the way we define the symptoms is very, very not so objective as in other diseases. We rely a lot on categories that they have some overlapping between the symptoms. They are defined differently depending on the country you're working with. And you have a kind of a subjective medical criteria, right? You have one decision that's a human that is going to, at the end, check and say, oh, it's or it's not. Of course, this depends on the country, depends on the nature. So, like the medicine is not uniform of other places. But it's definitely one very hard area of medicine because it's so much broad, the things that you can decide what's going on, and it's very hard to actually determine, oh, this is the case. But at some point you have, right? But then the biggest issue on that is that there's a huge opportunity for abuse, because if there is not like a blood sample that you can take, oh, it's 45 or something like this, and even if the symptoms there are overlapping between the diseases and some people really need the attention and everything, it's a place that's very easy to find people that are using it non-significantly. So now coming back to AI, so how can we actually bring AI into this kind of problem? So what are the characteristics, what are the features of working with psychiatrists in the sense of AI? Remember, when I'm talking about AI is a very general term. So here I'm basically talking about building tools that can help the psychiatrists in some of their tools. So I use the word diagnosis, but it's definitely not right. In the sense, I don't want to build a machine that does a diagnosis, but more like a diagnosis assistant or something that can actually help identify the cases that need more attention. So it's not, I'm not talking about tools to actually replace the doctors, but at least help them a lot into the sense that you have many people that need help. But we are talking about a problem that has, and is no quantitative data or very limited quantitative data. Right? You don't have the blood sample for many of these problems. The mapping of the data to the labels, it depends on some labeling that is subjective many times. So how you actually decide if a person has one issue or not is because one doctor just said, listen to it and said, oh, yes, he had it. And that's an area that is very sensitive. So there's a lot of resistance from patients and doctors of actually having a machine or having something not human involved. Although I'm thinking about taking out this part, because actually most of the people that I've been talking with, most of the time they were very receptive to have some help, especially from the public sectors in Brazil. So for the ad, this is really hard problem. But it's not completely non-quantitative, so there are ways of actually making exams about the mental state, about the cognitive capability of this person. So there's some standardized methods. For example, this is the mini mental state exam that you essentially make many questions that you can start to examine. Oh, the person knows where he is, the person has an idea about the time, about the space, about some areas of memory, and this gives a kind of a value. There are some of these like for depression, like the Hamilton Depression Rating. There are some for anxiety. So there, psychology area, there are a whole range of these values. So this already gives you some numbers to work with when you're doing some machine learning, right? But it's very limited in some sense, right? Just give you a number that it's not always very objective in what you want. So what we've been working actually trying to use AI is this type of analysis that we call critical discourse analysis. There are different names around, but essentially, analyze the dialogues, the discourse, the speech. So the person, the patient, the user, it's evoked through speech. There are many ways we can actually evoke. It can be a dialogue. It can be describe a picture, describe something that happened in the past. And many doctors are actually trained during the residency. They're trained to identify by the sound, by the way the person speaks, but what the person speaks in certain context, to actually characterize if it's a mental, if it's a mental illness or not. So here's the basic agent of decisions, the doctor that will listen and make a decision based on what he's heard before, right? So this is an example. I think most of you might have seen this in the movies or something like that. Rorschach test. This has been out from the 20s or something, and when I started looking at this, actually data that's from the Wikipedia, not so hard, but it's striking how this is very well accepted, especially in the legal systems. Like, I did a kind of a check in Brazil also. It's used. Essentially what they did, like they have a set of figures and they did a huge sampling. They gave to a lot of people and said, what do you see there? And they had the psychiatrists and the psychologists checking, if he has some traces of behavior, some traces of mood and everything, that they can make some profiles, and they just made a statistical reference. So, okay, if it answers like this, then it has this trace. And this is extremely accepted in the, for example, this one that this court, using court was only once one of the lawyers complained about it. So that's not something so hard for people to actually accept. So this changed a little bit what the problem. So now we have at least some input that we can work with. So we can have some quantitative input in the sense that you can apply a standardized test and have like a score, but also we can have some testing. We can ask people to speak, we can ask people to write something, we can analyze that and check if we can have some features. So thankfully, now we have, not now, before me, we already have a lot of tools and AI to work with language. So we talk about this general area that's called natural language processing, although AI now has it becomes huge. On my side, I started working with this before ChatGPT, so it was not only trendy. So let's talk about the works that I started doing and what we actually do in our lab. So the Dr. Natal Mota is actually the psychiatrist that got my authorization to get the job. She would work with Professor Cesar Renno, that was nowadays is a big scientist star in Brazil, because he wrote some books about dreams and sleep. And I collaborated with him in a lot of modeling on this work. But then they started analyzing, if I'm gonna ask someone a question to speak, what's the best question? So what's about the best predictor or best evoking to find some of the issues in the speech? So they started working with schizophrenic patients, bipolar patients, and control patients into taking questions. This is a very characteristic of this kind of study. It's very, very low number of samples. So it's a very hard problem with very low samples, so it's definitely not something very easy to work with. But then they started asking questions like, and compare how. If I analyze the answer, what's the best question to actually have a better outcome in the answer? So they asked one of them to describe the recent dream. So what was your most recent dream that you had at night? So can you describe the activities that you actually had once you woke up? So they had like a battery of questions like this, and then you have just an answer. It's always a text. That is some sense. So the thing that this was introduced by Marco Pelli, but we've been analyzing this kind of things that essentially what they do is they take the whole speech, take like a graph, as each word is a different edge, no, and they do a graph. So whenever you're speaking the same word again, they just put it back. And this gives you a graph that people from the physics can work very well, in the professional also, and they can extract from that features from the graphs. So each of these features has some differences regarding how long does it take for you to come back to the same words and the length of the sentences, this kind of thing. But they didn't, at that time, they didn't think much about the what does that mean? It was just like, can we just build it and use these features? And what they can actually show is that for this comparison, when you have schizophrenic against control, like one of the others, also the others, you could actually, if you take the statistics of some of these features, you can make a difference. You can actually make a quite well prediction of whether that speech was from a person with schizophrenia and control. For the more dementia like this, not so much. Which was interesting. So actually they started looking for other things. So actually they started a whole line of research based on that. That one of the most interesting things that using this kind of strategy, but also, for example, giving images, so we can give images from the standardized data set, so negative images like air crash or something like this, positive images like dog, and neutral is like a train station. Right. So they were analyzing that, and they could find, for example, they could identify most of the people that would have a first schizophrenic event like 6 months in advance, which was quite interesting in some sense. So we've been working also with other professors now, Professor Lillian, that she actually works more with aging. So we've been applying the same kind of strategy, but more focused on checking cognitive decay, if it's like abnormal or normal cognitive decay. So this can be applied in different areas. And also the approach here is quite different. So we give like a small story, so the person has to tell what's the story that's going on. Some of the answers are like, I have no idea. So it's not so easy sometimes. So just to give an example, for some of the works that we've been working, this is kind of the image. This is very classic. It's called the cookie jar test, that essentially they give this figure and ask you to describe it. So what's going on? It's very problematic in some sense, like in Brazil, cookies is not such a big thing. Like we don't have many of this grass in the back, so it's a very American or something movies thing. So, but it's been somehow standardized, and it's been used in this big project. It's an amazing project that they're starting to normalize the methodology, so we can have the same data, the same speech discourse from different contexts, different areas, all in the same place. That's essential because it's so hard to get this data because of all the process that having a lot of data, it's really nice. But from the point of view of AI, one of the things that had most impact was this address challenge that essentially they have that cookie jar problem, and they just released some of the sounds and some of the texts into a competition. So this really increased the interest in the area. A lot of samples for the this nature of the problem. And then you go to the competition, I got 0.3% more than you, or something like this. So just an example of one type of work of this. So we actually engaged in this kind of competition. So this is Marina, one of my students. This Professor Aline and Rodrigo, both are now at Exeter. When we started, they were in Louvain and Sheffield. But the Newton Fund was basically financing me starting a collaboration with them for this kind of work. So we essentially started using, well, we had all of these new transformers models, BERT, GPT or something. Can we just use them? So these models, essentially what they do, like you put all the text here with some pre-processing, like becomes a kind of a vector into embeddings, dimensions, and then just use that and apply at the end some classification just to see what happens. And the beauty of that, that when you can actually apply to some of this is for the, this is one case, like not 99% all the time, but in general, you got a result around 85, even 90% of accuracy in actually detecting one of the problems, which for me is very surprising. Kind of works quite well, and this is. But when we actually apply the graph, they call it the connectedness of the speech, you also get more or less in this range, which is quite cool. But there's a big problem with this, and even with the connectedness. So we can actually give this to a psychiatrist, something like clinics. You basically have like a black box that's saying, oh, it's bad, it's good. Right, and if you take like this image to anyone without any training, even if training, it doesn't tell much, right? It's not really intelligible in any sense, but it gives you at least a sense of, well, it's separable. So I can actually look at the text and say, oh, there's something different in that. So the first thing we started looking, so can we use the system to actually give some sense of what's different between these two things? So that's a nice thing about NLP, because they already give us a lot of tools to work with that. So one of them, like for instance, we can use some of this feature, some of this tool that's called semantic similarity. That there are tools that can give a sentence and give just a value of how close is this the similarity between two things, like for instance, a boat is a transportation modality. So we can have like life is like a boat, stumbles are part of life. It gives you some closeness to that. Also, some like you can have like classification that you're not comparing two sentences, you're comparing one sentence into one label. For instance, you can have like I could die for an ice cream. And then this is a very positive sentence, and so we can have this kind of association. So some of the studies that look how maybe if you're looking to depression, you can see how many negative sentences, this kind of thing. But at least it's something more than just it's one or the other. So also you can have some more fancy stuff like top key modeling. So you can take a whole sentence, and it will automatically generate some of the words that are more prevalent, some of the cloud of words that actually can help. So all of this kind of helps for you to at least know what's different between the two of them. So one of the works that we started to do on that was, many people did that before, really looking into, okay, I know they're different, so what's their difference? What we started looking is to use these new tools of explainable AI. Explainable AI is this branch of AI that we actually want not only to make decisions, but also know why we're taking decisions, or at least know what's different between the two the two things that you are comparing, and what was important in this decision. So two important terms here are interpretable. Interpretable means that you know exactly why the model took the decision. And the other one is explainable. Explainable means that I don't know exactly why it took the decision, but I know features that were important during the decision. So here we're going for explainable because you cannot interpret the ChatGPT and all this stuff, not yet at least. So what this integrated gradients essentially does is, let me here. So here's one example that I can have, like, these are clearly not real samples. This is just for illustration. So we can have like two subjects and a different phrase. So essentially, we tokenize, we turn the text into numbers, into embeddings, and that we just throw it into a neural network that will give you some score that you can classify as Alzheimer or not. So what integrated gradients does is that basically it goes away from the end to the beginning and gives you a sense of how important was that input for the decision, and what's the direction of that decision. So the nice thing about this is that at the end you can have a glimpse of, well, this one is really helping to go up, this one is really helping to go down. It will lose a lot of sense of the relations between them. So for that we would need to see the internal part, but at least it's like the first approach. So with this, I can give an attribution to each of the figures. And for the attribution, I can actually look, okay, it's a word. What's the feature of this word? What are the labels that I can use on that? So for example, I can say, oh, it's a substantive or it's not a substantive. I don't think it's right. So just the linguistics just kill me with that. But just to give a sense that now I can use a label and check whether this label was important or not. But then for me to give it a label, then also I'm glad that the people from the linguistics, psychologists, and all already have some standards. This is very controversial in the sense that there's a work that is called LIUC, that is linguistic inquiry word counts. That is basically takes a word and gives a label, and then counts the label. But there are some labels that are related to emotions, like, oh, this is positive, this is negative. There are labels for linguistics, oh, it's a substantive, it's a big word, it's a small word. So there are a whole set of words, but the nice thing about that, they all have a description, so they're very good candidates for explainability. At least I can say, look, there are many big words in this speech. So what we basically did in this work, we put these two together. So I have one word that I know if it's important or not, and I have a description system that can give you labels, or that are at least explainable labels. So what we've been doing is really take like the samples, apply the training, so we can actually train it and make the separation. Oh, this is Alzheimer, this is not. We've been taking the attributes and checking, is this feature really pushing to one side or pushing to the other side? This is an example of of feminine words, like she, her, Maria, or something like this. Comparing here, so it's just like a distribution. If you take all the words and the female and the attribution, so negative goes to Alzheimer's to control, and positive goes to Alzheimer's disease. And if I take the amount of words that are feminine and just sample other words, I can, like, in average, so this is like 10,000 random permutations, I would show that the average attribution associated to feminine is very low compared to the distribution. So this means that these words, the feminine words, they are pushing towards control. Sometimes it's more like they're appearing more, not only appearing more, but they're appearing more in positions that are important for the classification. And the other thing we do is just asking the question, is this really helping the classification? So essentially we take the curve of the classification And we only use this, we mask the other words, we only use the feminine words and check whether the classification gets better or gets worse. So there's like a distribution of random masks around all of the words, and this is what is the classification I would get on using only the feminine. This shows that if I only use the words that are feminine, they give me a better classification than if I just take some random words from the classification. So using this tool, the next thing that we can start asking, are these labels important for the classification? So this is like for the cookie jar test. It's well known that reference to feminine because there's a huge feminine icon there. So people will typically talk about the content, right? So this is not new, but it was interesting that we could get in a really strong statistical value compared to the literature. But also, like if we apply it to the Portuguese, so the Portuguese test is the dog story that it's been also described, but also has a very strong feminine reference. That's the model that we use. So which was quite cool. So with that system, we can make this kind of plot and check, okay, for the Portuguese and English different tests, what are the classes of terms that are actually important for the classification. And what we found is essentially that social references indicate difference. It's not new, like something that's quite new in this sense, because these are very social images. But it's really nice to have a tool that can really bring it like different languages and everything, and really point out which are the different aspects that can work with that. This work, my student will submit it until the end of this month, so you can look for our name probably in your apps or something like that. You have to until the end of the month because of the grant that's finished, so it's fun. But then it gives, okay, now I have a tool for explanation. Okay, oh yeah. 20. So now, okay, we have a tool. So this we've been applying a lot in the sense of like a clinical applications, like trying to convince, and also have some feedback of people in psychiatry. How can this be helpful? How can this really help in their work? But there's a problem with that. Okay, I just jumped this. Just saying that we're getting better than the beginning of the talk. But then comes to this point, right? Is this enough for it to actually come to the clinical and be helpful? We've been partnering with some hospitals that they've been applying that in different ways for identification and everything. The feedback has been very good in some sense, like some of the physicians are interested, but it's always a mystery. It's always we have this new tool or something like this. So one of the problems are, so what's missing? What we actually need for this to have actual impact, to have like a tool that can analyze the speech and everything. So I'll do an analogy, for instance, when you're doing cholesterol tests. Right? Everybody goes to the doctor, wants to meter something, collect the blood sample, and then you have like the lipids summary, give you a number, and if it's high, it's bad, if it's low, it's bad. Everybody knows that if it's high, it's bad, right? But why? It's not because of the number. It's essentially because we know the mechanism. Right? It's always told, oh, you can have fat in your veins, you're gonna clot, and then you have a problem with that. So we are measuring that. So it's a very direct connection. So when you have a lot of fat in your blood, you can relate, oh, that's not good. Right? So that's essentially what's missing. Right? So if I can say, oh, the person is speaking a lot of feminine words when not speaking feminine words when he's in vocal, it's a little hard to tackle, but essentially because we don't know the mechanism. We don't know why, what's missing. So why is the person speaking strangely, why it's missing, why it's talking more about the abstract than more precise words. So that's when computational neuroscience comes. So for this to actually be impactful, we need to be able to explain how is the speech being generated, how the language being processed, and build models that generate language, that generates language in a non-typical way, right, that we can relate to schizophrenia, to something like this. I'm not saying I did that. I'm saying that's more or less the direction we're trying to do when we're doing computational neuroscience, but this is really something important to be done. So essentially the question is, what do we actually need to be able to simulate this behavior that we can observe? So we can observe what people speak, we can observe how they speak, how they make, but can we simulate that? Can we actually point what are the parts of the brain that are important for a certain response, or something like this? So just before, when actually this paper was our seminar thing for this, for getting this grant, that we started to make this question a little bit before ChatGPT. Can we actually build a model that is neuroscience informative about how you can represent or generate text? So the problem about working with a GPT or working one of these things that we can actually, we've done that, we actually published in some conferences. We can take the GPT and make a change in the attention layer, kill some neurons or everything, and then emulate not so good speech. What does that mean? Like, it's really hard to make any relation about what's going on in that model and what's going on in the actual neuroscience model. So we wrote like this paper trying to make at least one trial, like one hypothesis of what are the important neuroscience mechanisms that we can actually apply. This was our last paper with John Lisman, who was kind of a supervisor, and it was like his last thing that we started to work with. So essentially which was really nice because we could take some of his works in neuroscience and start to think about what do we put after step together. So our suggestion, so we essentially took a lot of mechanisms, networks, or phenomena that we know from the computational neuroscience and neuroscience that can do some processing in some part and try to make a more integrated version that at the end could represent language or something like this. So one of the concepts that we started to discuss is this idea of actually have a compositional code. The idea that you can take one action like the tall man ate a lemon cake and make this into a more like episodic memory form. So our first proposition was, okay, the brain must be capable of doing something like that. I really take like a phrase that it's in a sequence form or in a long form and turning it into a unity representation, like ensemble representation or something like this, that it's represented at some place. And that sort, we've been working a lot in different models and how can we actually put many dimensions into that. So there, if you take the whole literature of place cells, grid cells, and this kind of more representation, they are all about that. Like how can you put many informations into a single concept? This relates a lot with the embedding concept of like how you actually make one, how you turn one concept into representation that relates with others into specific space, multidimensional space. So we've been working, so all the work that we and many others do into this, building this very precise neuronal models, this can be very informative about how you can actually take many informations coming from different areas and conversion to a single representation. So the key questions here is, what's the brain representation for this embedded space? So there's a whole field for that. We've been playing a little bit with this. So then go to the other place. Okay, I can represent one concept from one phrase or from one thing. And the beauty about that is that even for translation, it's quite easy. Like if it's a compositional representation, it doesn't need to be in a fixed sentence like in Portuguese. It can be in a more compositional sentence like German. Or, sorry if I'm saying something very bad. Like I don't know if Germans, but they have more like Japanese. Like they have a different structure, but that at the end will generate the same unit, the same computational unit. So the key idea here, using many models that we publish and work with, one of the ideas is that you need a buffer. In some sense, you need synthesis. You need really to put one after the other after the other. Like the idea of the knowledge is that you have one unit of knowledge that it's someone did that or something happened. This is that, and put that in sequences that can make some proximity. And I will discuss briefly that we can work with that. And the beauty of working with this model is that you can actually project that into a neural state that they have some distances, they have things that can work with. And this relates very much with much of the literature in computational neuroscience. When they're talking about attractor space, like this, the word now is manifold areas that how can you actually have a multidimensional space in the brain that you can project some information that's knowledge into something. So like the whole computational neuroscience field has many tools to actually implement that. And the last part is, okay, how can I make a question and get an answer from that? So essentially the question will be when you present a partial knowledge. So I know that something happened, something is missing, but then you have a memory that I state in your brain that you can actually project into that and collect whatever is missing. So in this paper, we kind of described it in more details about timing and everything, but I just point to some of the work we've been doing. So how can we actually implement that? For instance, one of the work that Professor Marco is doing, we're like finishing one PhD student work on that is, how do we actually take that input that is already like this compositional representation and put it in sequences in a way that we can explain that in brain terms. For example, what we've been working a lot in Professor Marco and John, they published a very important paper in the 90s about brain oscillations. So how you put this gamma oscillations that it's about 80 hertz into the theta oscillations that it's about 8 hertz or something like this. Ranges a lot, but they are always coupled in a way that they show that this could be a mechanism of actually implementing these different sequences. So they published some work there, I published some with them, and many people like Hassamo and other researchers, they do really interesting work of kind of computations that you can do with this kind of system. Like, for instance, to maintain a working memory, so it can, with simple neurons, put in a way that you can insert one item, then it starts, and then insert another one, so it starts in a buffer. Oh, the buffer is full, then the last one goes in a way that you can actually maintain it in a brain state. So, for instance, it's very important to maintain something in the head, right? So there are a whole field of research in these oscillations and working memory that can fit into this problem. And another problem that I've been tackling with is, okay, I have to put that in time so I can represent some compositional into one memory state. I can put that in time, but I also need to make decisions. Like, oh, I have I saw a guy eating an apple. It could be a pear, it could be watermelon or something like that. So I have to make a decision to put that in memory. So there's a whole area of actually how do I implement that with a neuromorphic computation paradigms. Right? It's very easy to do in Python, like just select one, but to implement it in neurons are some things that is not so easy to do. So just a glimpse, so here just a glimpse of the mechanisms that we actually need to start think about implementing some of these decisions. And here is just an example of how this would at the end work for answering one question. So here's an example where you have like this facts, like Rusty ate a baguette, John was cooking scallops, Ol was baking pizza, and Boris ate the chocolate. So this is like a contextual thing that how many things happen at that time, and then I can ask a recall on that context if I give a partial information. So here I just giving like, oh, John was cooking scallops, Boris ate chocolate, Rusty ate baguette. So here an example that we, at the time, we were related to read cells and all stuff, but some part of the brains that they just got the Nobel Prize at that time. So it was very trendy. But this is just an example of how we can actually have a lot of partial informations about the brain that they actually implementing one context that you actually experienced. And we did like that because there's some part of the brain, like the grid cells, where you have you don't have a very specific information about a place. You have information about many places that they're kind of related among each other. So it was just here we were just trying to relate how we can actually take the more like a language compositional information and relate it to something that people do with rats in a spatial relationship. But essentially, this is just showing how you can actually have, if you can have some attractor dynamics or some dynamics that will converge into a brain state, then we can have some answers out of a knowledge that you're already trained. So one of the things, I'll just pass that, it's just some example like, did Boris drink beer and donate the cake? And then you can essentially say, oh, no, because they don't fit, I cannot find this memory. Or if it's missing a memory, I can take something. But this is an example of work I've been doing into this direction. So can we build a whole network that we can converge into state, or at least check that state is not there? So most of the thing I've been doing was in grid cells, place cells, because that's where we have data. We have very few data, something like that. With language, it's not so easy to put the needle in the human brain and ask them to speak something. Although people are doing that nowadays. But that's a huge reference we have with rats. And it's really nice, actually, you can make a lot of analogies between what the rats, the brain rats are doing. And the last thing, like, so with all of that, can we build a model that actually makes a decision? So that I work a lot with Dr. Incarni from Melchi. She specializes in models of decision making. So if I can have a representation of a context of something, put them in sequences, compare with something I had in memory, with something that I just did that was, we don't know. Can I decide which is the decision I have to do? Like say no, say yes, say okay, or something like this. So this work actually in our university, we have a center that specializes now in using psychotropic research for depression, for psychology, and everything. And they came with us, look, we have this whole data of people doing, they actually gave LSD to people to do memory tests. And they said, okay, can you make some relation with models and everything? So it was interesting to actually build a whole model about decision making using to fit human data. It was quite nice, actually. Interesting. I did not participate in an experimental part. So the situation is that, like, the message here is that there's a lot of impact we can actually do. There are a lot of things that have to be talked with the psychiatrists, with people in the clinics. But it's not only about bringing the tool. Like it's not only say, oh, we have an AI and it will flag and it work or not. We really need also to bring what we've been doing in computational neuroscience in the direction that we can use it as a way of describing the mechanism. So For instance, we've been working a lot with differentiating if a person has a problem in the way they speak, or in what they speak. And this can be very different from one disease to the other. We've been tackling some of the problems that are even harder, for instance, to detect depression or conditions that not even detect is a very strong term. It's really like to give hints that the person might have depression, but also, for instance, to detect situations that need some intervention, like life-threatening situations, which the text is much more subtle than if you take, for instance, if you take someone with schizophrenia, like in a very strong state, it's very easy for us to actually identify. But there are also a lot of different problems that teaming up with the UK changes the issues. For instance, in Brazil, we have the diversity of people with different literacy levels, different social cultural levels that it's slightly more diverse than here. And this changed a lot. Like if we're talking about what the person speaks and how they speak, many times it's really just a way of speaking, how much they were trained. So there's a lot of problems that are just about this discussion of really AI directed, but really the AI alone cannot be applied if we don't have something that we can really relate. So look, the mechanism of Alzheimer's, how it's impacting in this region, if that condition is changing, the oscillations is changing, something like that. Pinpoint direction. So thank you. I just wanted to thank again the sponsors of the picture for the report. Thank you very much, everyone. Welcome to visit Natal. This is the typical weather there.
So we have time for a couple of questions in terms of
Very much. Beautiful. Very interesting. I was supposed to go back and ask you about the Alzheimer's disease with the language modeling when describing the cookie jar picture and the other picture of the Portuguese study. And I was wondering a little bit about if you have data on the socio-demographic makeup of the control group and the patient group, and how kind of thing about gender of the speaker might affect things like the use of feminine words or even the age of the speaker and things like that, and whether that was something that you looked at.
So the biggest issue is the sample size. Like we've tried to make some of this analysis, but most of them just statistics. So some are because, but like they're normalized in the sense, like for instance, for our data in the Brazilian, they're all from the same clinical center. They are a group of elderly people that are more or less homogeneous in terms of social background, so they are not illiterate, for instance. So it's more or less homogeneous. It's controlled for that. And this address data set, the one in English, it's from a bigger data set that they actually made it ready for AI by controlling maybe like gender equal or something. There are a lot of differences in gender, known differences in gender in these diseases, especially in the incidence. But for the analysis now, with the amount of data in the Portuguese, it's like 56 samples we were working with. So it's very low. It's very low. It's really like actually what we've been like. Most of my work nowadays has been okay. Can we extend that? So we've been approaching a lot of clinics. Actually, we've been trying to work a lot in making a standard tests and standard setup that you can bring to a clinic and start asking people to play with. And I think it's not only language. There are a lot of things that, like, when you're working with someone, like the way the person speaks, the way the person reacts, is also very important. So we're trying to work with also behavioral We must be very certain before we start collecting data because it's very troublesome. But nowadays they should produce really very low samples. So that's also an important point when I talk about 83% occurrence or something like this. Like it's a very, very small data set, and I did not collect them. Most of them, we don't know who collect them. There's some pre-processing, so sometimes even the pre-processing, it's easy for you to add some something that will repeat.
I was actually about to ask very quickly, with the small sample size, are you even able to make separate validation test sets to avoid overfitting yourself? I mean,
what we did, like we do like a 5-4
cross
yeah,
validation.
5-4 cross validation. At my work, at least, I'm not so much worried about accuracy in the sense like, oh, this is the best tool or not. In the field, they are, but it's like, you know, like this Congress, and they won't have the best model or something. But from my view, is at least like it gives you something above chance, so I can really say, look, there's some difference there. So what I'm trying to say, what's different in some sense, but like I don't think I have a tool to actually take one person, use them, and then you say, oh, he's that or not.
You mentioned briefly topic modeling. I was wondering if you did some more studies on maybe classifying what would be the difference between a patient with, I don't know, Alzheimer's disease, for example, and the control, because I feel like in topic modeling, we care a bit less of accuracy measures, and it's more about the content itself.
So the idea about topic modeling is that nowadays how we inquiry for the labels is like a professional who will say, I want to see what's the impact of positive. I want to see the impact of negative. So when you work with topic modeling, you're kind of doing non-supervised training on the data set, right? To look, this emerges as an area of significance that it's interesting. So I had one student work with that, but we didn't move much further because he got much more interested in history and literature than actually in brain disease. So we've been applying that to processing tests of history, this kind of thing, trying to look, for instance, how the different topics change over time, especially with the Brazilian culture. But my first idea was that, so we can do something more automatic that we don't depend on the bias of the analyzer that's saying, oh, this concept might be more important than that. But that would be the idea, but we didn't go much further.
Yeah, this is very interesting and maybe useful in the future too. And I guess it's probably nowhere near the kind of accuracy you get with just doing a mini mental state, for example, like diagnosed Alzheimer's. But I felt like maybe that the early model that you're using is kind of maybe missing a lot of data that you kind of pick up when you're listening to a patient in terms of the concepts and things that the person. Whereas I think the model just uses individual words. Is that right? And
yes.
So that's I felt.
This is very.
I don't know if it's the way around.
I completely agree with you because this was the first approach. For instance, this connectedness measure, it doesn't tell much about you and about the. And imagine like we are just taking the way the person speaks and turning it to texts and then processing it into. It's definitely taking much of the information that you might be useful. But as a first approach, it makes sense in the sense of AI and already gives some hints. For instance, one of the proposed applications is really like, okay, if you have too many people asking for appointment, can we use something at the least to identify, look, this person speaks very well and everything, so might not be the most extreme case. But for instance, what I'm mostly interested into is this, how the speech relates with the content. So this will relate a lot of them. Basically, because I worked all my research career into memory models. So I wanted to see how the memory models would fit into this kind of thing. But if you take, for example, this test, like they're fixed, like the cookie jar is one test. The second time you do the test is not already, it's already biased by the first time. And so what I've been working with, for instance, we've been working on one project that we are trying to get rid of all the style of the person speaking and really looking into the content. So, like, if the picture has a train or something, does the speech really relates to some of this? For like the Hochner test and for the cookie jar test, these are like, we have professionals that they look. He should talk about the woman. He should talk about the kids. He should talk about, and they can make like a list and say, look, he saw that and he didn't talk about the dog. So what we've been trying, I'm focused really on, can we take it like a regular picture that the person never saw it before, use AI to actually interpret what's the content and see if the person speaks in a way that you can relate to that. I think that will be very much more helpful than just a maker. Just to say, look, yeah, AI could identify something there, so the person also identifies something. But this early things were really focused on small tokens, which is problematic. But now I really wanted also to add this expressions and like without an eye tracking, like just to see, is the person really looking for, is the person examining the image in the way it should or something? Because it's been so cheap compared to 10 years ago. Could be useful.
I'm a clinical psychologist, so I work with couples. To what extent you can use these models to analyze interactions between people?
So some of my colleagues, not me, what they've been actually using is they actually put like an AI listening to the. They didn't do couples, but what they did was
Or a diagnostic interview.
Yeah.
Asking questions.
Just at least, like, for instance, one of the problems for clinical doctors is to remember what was being told. Like, you have to be like make annotations. Oh, he said that. So he can use these tools, for instance, to make a summary of, oh, look, during this conversation, he did that, and something. For this, like here, we are kind of for the diseases, it's more about detecting if the speech is not so much into the standard. Like, oh, it has a lower performance in the fluency, has a lower performance on the content, that we know what's the content. But what, for example, the work we've been trying to start, to do with depression and this kind of thing, it's really trying to look, okay, does the speech has some characteristics of aggression, of depression, or something like this. So I could imagine, for instance, one situation that you have like a couple or something, and you could at least look, he's speaking to her in a very aggressive way, and or she's being very negative, or he's being very passive, or something like this. Like, it's the kind of thing that you can do, but it's still very automatic. So in some sense, that there are a lot of things that could be done, but it really have to mimic what's been doing in the clinics. But most of the time, we need to say, look, they have a problem, so please go to the clinics and have a conversation. But first, a big area for this now is applications, so people can actually do it at home. We're working one with the elderly people, that it's like an applications for doing cognitive exercises and everything. And then in the middle, we are analyzing if the person, like, oh, how was your day? And then seeing if you can make this as something that gives you a hint of something that's happening. It could be like in counseling, maybe like a journal of the couple, and they just say the journal. Like the nice thing about this kind of models is that for security and privacy, like you have a machine that's analyzing the speech. So it's not coming to someone that maybe I know him or not. So it's a machine that analyzes and says, well, that's been very negative description. So this can also go to the doctor sometimes. Look, it was a very negative speech. Doesn't need to come with content, right? So this could be a very interesting tool for like the time they're not at the clinic, right? They're taking data or something. It's a huge field. Like actually, like we're always having ideas of how to implement them, but we are actually still on the foundations of what we can actually do to analyze the speech.
Okay, I'm mindful of time and we're running over a bit, so thank you very much.
Thank you very much.